Yeah, okay. So let's start. Hello, everyone. Welcome to the next meetup organized jointly by quantum computing groups from Washington, D.C. and Warsaw. Today, we have great speakers from Xanadu, Tom Bromley and Catalina Albornoz. And the title of the talk is Quantum Machine Learning with PennyLane and Xanadu Quantum Codebook. So this meeting is recorded and there is also live streaming on YouTube. So the link was shared by Helen, and hopefully we'll also later share the recording with you. If you have any questions during the lecture, please post your questions on our chat, preferably here on Zoom, but we'll also try to read and ask questions that will be posted on YouTube's chat. Before we start, we would like to announce some other meetups that will be organized by our group. So the next meetup will be on 26th of February, and the next one, 5th of March, quantum circuit optimization. Later on 12th of March, there will be an interesting lecture from numbers to tensors, a brief history of effective abstraction. At the end of March, Zeki Sesker will give a talk about quantum science-oriented approach to introduce quantum computing to a new audience based on experiences from Qaoa and Turkey. We'd also like to thank our partners, sponsors, Quantum AI Foundation, the Warsaw Quantum Computing Meetup. So together with Sebastian Zając, second moderator, we are both representatives of this Warsaw Quantum Computing Meetup and Qaoa. Also, Quantum Computing Group, Quantum Computing and Data Science group from Toronto. It's one of our partners, Zen for Quantum, Orion XNet, Association Quantum, Cambridge Quantum, Q Egypt, another Q cousin from Qaoa, as well as Q Mexico. And that's all for the introduction. Tom, Catalina, thank you for accepting our invitation. It's our pleasure to have you with us. And if you are ready, the Zoom is yours. So I guess that Tom will start.
Thanks, Pavel. Yeah, great to be here. Thank you very much for inviting us. Just give me a second to share my screen. Okay, here we go. Stop me if you can't see this. So yeah, hey everyone. So this talk today will be a mixture. We're focusing on quantum machine learning and how you can do this in PennyLane. There's kind of three parts to the talk, I guess. So there's a QML part, more sort of theory and slides based. There's a PennyLane part where we're hopefully going to be coding together. So some live code, doing some QML in PennyLane. And then finally, Catalina will take over and show you the quantum codebook. And that's a super exciting thing that's just come about fairly recently. So yeah, feel free to stop us if you have questions. We're happy to pause. It can be more of a conversation than just us talking to you with slides. So without further ado, let's just frame the quantum machine learning part within the context of PennyLane. So we define PennyLane. This is our sort of one sentence motivation. PennyLane is an open source Python library for differentiable quantum programming of near-term devices. So the bit that I want to highlight is the differentiable quantum programming. And to understand that, let's first take a step back and think about what we mean with differentiable programming without quantum. So what is differentiable programming? I mean, I think there's probably a pretty fancy explanation on various different viewpoints on how people interpret differentiable programming. But for me, it's really just, I guess, the abstraction of quantum machine learning, of classical machine learning, of standard machine learning, where we have, say, a model, perhaps a neural network, and we define that model to be a composition of operations. So in a neural network, you might have, say, a layer going on to another layer, maybe a convolutional layer, maybe a recurrent layers, all these different types of operation that you can have in a neural network. And each one of these operations together provide a computational graph. You can talk about like higher level neural networks, or you can drop even lower and think of operations on the level of, say, addition, exponentiation, or even like say a principal component analysis. So this idea of differentiable programming is describing a model in terms of these smaller, more elementary steps, capturing how each one of these steps can be differentiated, and then giving users the ability to kind of go forward through this model and make a prediction, but also differentiate backwards through. So yeah, for me, differentiable program is kind of the abstraction of machine learning. And of course, yeah, I think everybody's familiar with these three usual suspects: PyTorch, TensorFlow, and JAX. These are commonly used for machine learning or differentiable programming. So, okay, that's differentiable programming. How can quantum come into that? And of course, that's what we're interested in at Xanadu, and one of the key focuses of PennyLane. So let's go right from the start. I know this is probably pretty familiar to most of you, but let's think about a quantum circuit just from a very high level. There's really three components. There's the input part. You have some state, typically it may be a product state over, say, zeros, but it could be, say, a state coming from another device. We have the middle part. This is some transformation. So this could be described by a composite unitary U of theta, but typically, and I guess even like in practice on actual quantum hardware, this composite transformation needs to be broken down into these elementary gates. So we have some input, we have some processing or unitary transformation described by one or more parameters theta, and then we do some measurement to extract, say, the quantum information out of the system. So that's just a model of the quantum circuit. How we have this measurement, how do we actually describe this measurement mathematically? Well, it's as simple as this. This is just Born's rule. So we have our input state psi, we evolve it with this unitary U of theta. We get some, say, psi theta, some psi primes. And then we sandwich that with B, the observable in the middle. And this gives us the expectation value of some observable beta that depends on our parameters theta. So yeah, this is, although it seems maybe, we're used to thinking of quantum circuits and quantum computing as very complicated and difficult to do classically. This is true, and this comes from the fact that this psi, this scales exponentially with the number of qubits. But when you look at it just purely mathematically, it's just a composition of simple operations, matrix and matrix vector operations that we chain up. I guess the U of theta can contain multiple matrix operations. So it's just a composition of well-established linear operations. And also these operations, I guess they depend on their parameters, theta, and the expectation value of B. It just sort of follows through that typically it depends smoothly and well behaved on these parameters, theta. So although we're used to thinking of it as a very complicated system, actually maybe more so from the perspective of a differentiable program, it's not so complicated to describe this expectation value. So that's really where quantum differentiable programming is coming from. So it's just saying, hey, let's create a circuit, a variational circuit, we normally say, so this green box here. Really, the output of the circuit is just some function of some inputs x and some controllable parameters theta. We can train, we can optimize, we can do all the things that we're used to doing, say, with a neural network or with a classical machine learning model, with a quantum circuit. I did see a hand up, by the way, so I can pause now if somebody has a question.
Yes, there is at least one question in our chat. Question from Samar: what does the observable does?
So yeah, so maybe this slide is the best one to see. So this B, the observable really captures, I guess, it's maybe even from when you do courses in quantum, the first thing that we learn is you're going to have to extract classical information out of this quantum system. And the only way that you can extract this information is via an observable. So the observable really captures this transition. And I guess an example observable is kind of measuring in the computational basis. So you can think of projecting under zeros and ones. That would be the more standard one, but you can have other observables as well. You can have an observable could be a Hamiltonian, so it could be, say, this Hamiltonian linked to a chemical system. So you're free to choose, but yeah, the familiar way is to think of sampling in the computational basis. Hope that helps.
Samar, I hope that it answers your question, but if you need any follow-up or clarification, feel free to ask. Also, Jairam had his hand raised, so maybe he would like to ask a question. Jairam, would you like to unmute yourself?
So I had a question, like in the back slide. So like, can you like explain that math to me? Like,
sure, yeah. So it's, you can think of the psi, this psi on the right hand side. This is just a vector, and it's a vector. Say if you had a qubit, it's just a length 2 vector. You can think of it as a column vector. If you had 2 qubits, it would be length 4. So it's a 2 to the n dimensional vector. When we evolve a quantum state, what we do is we apply a unitary, which is just a matrix. So if we're going back to a qubit now, you can think of your qubit vector being multiplied by a 2 by 2 matrix, this unitary. So that's the matrix vector multiplication. And then, so this is the evolved state psi primed. We then capture this expectation value by kind of making this sandwich. Yeah, I guess it's maybe a bit harder to explain that part, but it's essentially column and row vectors coming together.
okay, got it. Thank you.
Thanks. Yeah, it might be clearer to check out the code book. So that might be a good resource there.
Wait, what is like the code book?
Yes, so we'll talk about it shortly. The idea of the code book is to, for somebody who is maybe not familiar with quantum, or even if you have like some starter knowledge, it's a great way to get started and pick up quantum computing and quantum machine learning.
Okay, thank you.
So Catalina will talk about it. Thank you.
Great. So Tom, there is one follow-up question from Samar. So maybe if it's fine for you, maybe I will ask.
Sure, let's go for it.
One that Born rule equation, even without observable, will lead to an inner product, which is a classical value. Samar, maybe you can also try to unmute yourself and clarify.
Okay, so about that, like the only like that equation, won't that result in a collapse of like when that equation gets solved, it would lead to a classical value, which wasn't the reason why we were using observable in the between of that equation.
So without, you can kind of think of without the B just means putting an identity there.
Yes.
So that it's the identity itself is an observable. So with or without, it's still kind of measuring an observable. It's
okay,
just
okay. I think I get some idea about that.
Yeah.
Thank you.
Thank you.
Okay, great. There was one more question, but it looks that it has been already answered by another participant, so I think we can proceed.
Cool, let's go for it. So, okay, we have this idea, we have a circuit, a quantum circuit now, and we can evaluate it, we can get its derivative. So we can then even expand our minds further and say, let's get this quantum circuit, think of it as a node in a bigger computational graph, where you can have, say, classical nodes in the graph and quantum nodes as well. Line them all up, and you get, say, I guess we call it here this this hybrid model. So this is, yeah, I guess the keys to understanding this is the ability to go forward through the model. So you do say you evaluate each one of these individual nodes, classical and quantum, and you can do a forward prediction. But you also want to train this quantum or hybrid differentiable model, which is what you need to do is then take the derivative of each of these nodes. And now we can do that, or at least we can think about doing that, because we understand derivatives of the quantum nodes in this model. So this is this idea of a hybrid model. Why might you want to do it? I guess this is still an open research question on why would you compose classical and quantum nodes? But at least one starter explanation is actually when you look at all of the established near-term models of like applying quantum computing, things like the variational quantum eigensolver and Qaoa, all of those are really kind of hybrid models when you look under the hood. they often involve, say, some classical processing, some linear combination of some terms in a Hamiltonian. So really, I guess this slide is to point out that a lot of the things that we're already thinking about are hybrid, but we can even think of more if we want to get more exotic. So yeah, just to summarize, we now, instead of thinking of like, say, a quantum circuit necessarily, when we're talking about this computational graph, we talk about a quantum node, which captures the interface between classical data coming in, running something on a quantum circuit, and then getting a measurement and classical data coming out. It's just in the middle, this box, there's a quantum circuit going on. So that's the idea. And now to talk a little bit about what you might make from what, I guess, how you might compose your circuit in this Q node. So the language you'll hear a lot in quantum machine learning and quantum differentiable program is these variational quantum circuits. So what this means is we say, hey, we have a quantum circuit. Let's fix the layout of the circuit. So let's say, okay, we have some gates here. We have maybe some 2-qubit gates here. We fix that. But what we can control is the parameters for some of the gates in this model or circuit. So maybe you have some rotations. You could have a multi-qubit rotation as well. These may have some parameters. You can control them and you can train them. But in this variational circuit, we keep the structure fixed. And this has really evolved from, I guess, ideas that I've mentioned, VQE and QAOA. We'll talk about them a bit more, but yeah, I guess it's kind of inspired from those existing ideas. So just to talk a little bit about what's going on behind the scenes. So it's tempting to think of, we have this quantum circuit, we have some gates, they're trainable. It might be tempting to think of it like a neural network. So you might think of, say, the lines, each one kind of represents the passage of a neuron in your neural network. And maybe you kind of have this layer structure. So it could look like a neural network. And I've heard that a lot in, say, the literature and discussion. We have a quantum neural network, which is this variational circuit. I think it's perhaps a bit of a misnomer. So that's really what this slide is intending to say. It's still an open question on exactly how to think about these variational quantum circuits and how to understand their trainability and what their use is. But I'd say maybe don't be tempted to think of it as it's like a direct comparison of a neural network to the quantum realm. So this result that I want to highlight here from a paper from Maria in the Xanadu team. So this paper shows that if you have this variational circuit, there is kind of like a dual way to think of it as a kernel method. So if we look at the circuit on the right here, we have some data being encoded into our variational circuit, kind of going after that model that I mentioned where you have an input, some processing, and some measurement. So we have the 3 parts: inputting some data, processing, and then we get an output measurement. This is a variational circuit, and it maps nicely to this figure on the left. So you can kind of think of the encoding part. You have some data coming in, it lives in some input data space. So you have some features, it could be house prices or whatever standard. I guess you might have, standard problem from classical machine learning that you want to put onto a quantum device. So this will be the input data. How is this transformed by the circuit? Well, actually, we have a state, right? We have a quantum state that's evolving as we go right across this circuit. And this state lives in a 2 to the n dimensional complex Hilbert space. So really, we're mapping each one of our data points from an input to this higher dimensional feature space. And then we perform a measurement, which is kind of, as you can see in the diagram here, a measurement effectively draws a line in this space and separates out to, I guess, 2 parts of the space. The objective is that we manage to create our feature space in such a way that we can, say, classify the data. So we can pull apart the blue circles into one part of the space and the red squares into another. So that's the objective of, say, a kernel method. You can find a linear classifier that separates the 2 classes or multiple classes. And how's it working with a quantum circuit? Well, we're doing this high dimensional embedding, and we have control from the parameters to actually sort of smoothly morph or change this feature space. So as we control the thetas, the feature space will change, and there should be some set of parameters theta that allow us to pull apart these two different classes. So yeah, just wanted to highlight this nice result, that maybe don't be tempted to think of these variational circuits as a quantum version of a neural network, more so as maybe as a kernel method. So we've talked about variational circuits. I also want to mention there's maybe like a higher level of abstraction towards a quantum variational algorithm. So there's three components to a variational algorithm. There's the circuit, the underlying circuit. We've discussed this already. And then there's two more parts. So there's associating the output of a circuit with a cost. So that might be directly, I guess we have this f(x) of theta. This is the output of the circuit, right? We can have a cost function that's, say, a function that lives on top of that maybe combines the results of different circuits together into one cost function. And we also have a training procedure. So we have one or many circuits being run, we have a cost function, and we also need to define how we then train this model. So how we find the optimal parameters theta. So those are the three components of a variational quantum algorithm. I guess the ansatz part is clear. In terms of the training procedure, there is a bit of a question there, right? So the idea with a quantum circuit, at least ideally, is we have enough qubits that it's hard to simulate on a classical computer. Of course, we're not really in that regime at the moment. We have, say, 5 to 10 qubit circuits, and we can simulate on a standard computer. But we want to be able to push higher, right? We want to go to 50 qubit or 100 qubit models. And in that regime, we can't go on a classical computer. We need quantum hardware to evaluate the circuit. And in that regime, how are we going to train this model? So we have a model that is, say, a 100 qubit circuit, the output of that. We're going to need to differentiate the output of this 100 qubit circuit. So we can't rely on classical hardware to find this. We need to find a hardware compatible way of evaluating the gradient of this circuit. So is there a way? And fortunately, the answer is yes. There's maybe a couple of ways to evaluate the gradient of a quantum circuit. If it's small enough to live on a simulator, you can just evaluate it like it's using standard tools like TensorFlow and JAX, and you can just back propagate to this series of operations. But again, if we're at this 50 qubit, 100 qubit regime, we're going to need to do something more advanced. So one way is this parameter shift rule. And how does this work? Well, you can kind of see it here. You can find the gradient of a circuit just by shifting parameters forwards and backwards. And most quantum circuits are amenable to a simple parameter shift rule that you see here. So maybe just to elaborate on that a bit, let's take a step back and think about, I guess this is pretty simple. So just a simple trigonometric problem. We have a function, f of theta is sine of theta, and we want to differentiate it. So I think most of us or all of us know the derivative of sine of theta is cosine of theta. That's great. But you can actually pose this, so this simple trigonometric identity, as a sort of parameter shift rule in itself. So let's look at cos of theta, which is the derivative. Now, using some trig identities, we can rearrange like this in the middle here with the sine of theta plus and the sine of theta minus pi over 4. So this is telling us that when you have trigonometric-like behavior in a function, I guess maybe I'm being a bit not very rigorous, but this is a clue at least that if you have something that looks trigonometric, then there may be a way to get a parameter shift-like method of evaluating the gradient of this function. So, okay, this is sine of theta, so it's fairly simple. How does this actually extend to a quantum circuit? Well, I guess you might just have to take my word for it. But as a bit of a hint, a lot of these quantum circuits, you might have a rotation. So you might have a rotation around, say, a Pauli X, a Pauli Y, or a Pauli Z axis. And these rotations you can express in a trigonometric way. So you'll have something like a cosine of an identity plus a sine of something else. So this is where trigonometry comes into a quantum circuit. And if you go through all the math, you'll see that most circuits, essentially ones with these rotations, are amenable to the parameter shift rule. So you may have been wondering, as I was talking, hey, this parameter shift rule, it gives you a gradient, cool. but it looks a bit like finite difference. If you've ever checked out, I think if you've done like I guess maybe a first year math course on numerical analysis, you might be familiar with this finite difference rule where you evaluate a gradient by doing a forward shift and a backward shift. So yeah, it looks a bit similar. But to answer that, if you have already got some doubts, there is a difference. In the finite difference approach, we typically want the shift to tend to be infinitesimally small. So we kind of squeeze it to be smaller and smaller, and we know that the gradient will, I guess the numerical gradient will start to approximate the exact gradient. So in finite difference, we want the shift to be small. In parameter shift, we actually allow the shift to be a bit larger. So it can be a fixed value, say pi/4, like in the previous slide, or pi/2. It actually works for any value of shift. And at least on an exact circuit, if you don't worry about running on hardware with finite shots, etc., on an exact circuit, you can see that parameter shift gives you the gradient exactly, whereas, as we know, finite difference is a numerical approximation. So they do look similar, maybe suspiciously similar, but there is some key differences there, that we get an exact approach with parameter shift, and also we have control over the size of the shift, which gives us some resilience to noise, of course. If we try to do too small a shift on actual hardware, we won't really see much of a difference. So, okay, so we have this parameter shift rule as a way of evaluating the gradient of a circuit. And this is crucial. And now lets us sort of complete the picture. We can go forwards through the circuit, evaluate it, and we can also go backwards and get its gradient on hardware, independent on whether we can simulate it. We could do this on actual quantum hardware. So we have the full, I guess, approach to getting the gradient, and then also training the circuit. So we can train using, say, a gradient-based optimizer like gradient descent, or something more advanced. There are other options out there as well. So if you remember, we're talking about these variational quantum algorithms. And I just want to give a few examples. So I'm not sure if you've had any talks on VQE, the variational quantum eigensolver, before, but this is a nice example that fits into this picture of the three components of an algorithm. So the circuit ansatz, well, actually, maybe I'll just give a moment to say what VQE is, if you've not heard of it. So VQE is this problem of, say, you have a chemical system and you want to find the ground state energy of this system. So this has applications in a variety of things, like understanding batteries, understanding solar cells. So it's an established problem in chemistry, in quantum chemistry. And how do we use a quantum computer or a quantum circuit to solve it? Well, we map this this chemical system to a Hamiltonian. And the idea is that we then need to find a circuit that minimizes the expectation value of this Hamiltonian. And the minimum value gives you the ground state energy, and the state gives you the a way to get back to the ground state of the system. So it's like a mapping from a chemical system to a quantum circuit. And this mapping, or this approach of VQE, fits nicely into the variational algorithm approach. So the ansatz part, that will be a circuit that's somehow designed to emulate or look like a chemical system. So here we mentioned this UCCSD. This might be something to check out if you're interested. This, yeah, I mean, typically we want to preserve some sort of symmetry in the system. So say like we have a circuit that preserves the set of K particle states in the system. So that's the circuit part. There's also an ansatz, and this is, as I mentioned, you have a Hamiltonian that describes the chemical system. We map that to a qubit or a quantum circuit Hamiltonian, and we need to find the expectation value of this Hamiltonian. So this would be the B observable that we saw earlier on in the talk. And then finally, the training procedure, well, that is, we know how to run through this circuit. We get the expectation value. This expectation value depends on the parameters of our circuit. So we need to find the gradient. And then we can do an optimization by minimizing this gradient using, say, gradient descent. So yeah, here we have gradient descent, and we get the gradient through the parameter shift rule. So another example to mention is QAOA. So this is quantum approximate optimization algorithm. This algorithm is used for, I guess, combinatorial optimization. So typically graph-based problems. We have an example here on, I guess, in the figure on the right. So this is a max cut problem. So the problem of you have a graph and you end up partitioning, you want to partition the nodes in the graph in such a way that the number of edges cut by your partition is minimized. So we can see in this partitioning, we have, I guess, 0, 2 in one partition and 1, 3 in another. And we end up cutting through 1, 2, 3, 4 edges. This is, I guess, a bit of an aside, the max cut problem, but you'll see a lot of graph-based problems or combinatorial problems that can be addressed by this QAOA. So how does this, I guess this is just to mention another typical example of like a near-term quantum algorithm. How does this fit into this variational approach? Well, the circuit itself, I mean, maybe if you're not familiar, then it's not quite so informative, but if you are familiar, then of course the circuit is kind of set by this interleaved application of two types of unitary, these mixer and cost Hamiltonians. So there's also a cost function. So in QAOA, we end up wanting to, again, minimize the expectation value of a Hamiltonian. This time the Hamiltonian describes, I guess, the cost of the system. So we map from this graph-based problem to a kind of a cost Hamiltonian. And then QAOA, the objective is to minimize this. So, and then also, we can train it by finding the gradient of this circuit, this circuit ansatz here, and then using a gradient-based optimizer, say Adam. This is a more exotic version of gradient descent. So these are the two key examples that are well established, I guess. But there's also like a more general application of variational circuits towards machine learning. And I guess that's one of the motivations of this talk. And I still say it's a bit of open territory on the best practices for a lot of these. So what's the best choice of a variational circuit for quantum machine learning? What's the best way to embed data that we'll talk about in this slide? It's still open territory. So there's still a lot of questions. But one of the big questions, of course, is you have some classical data. It could be, all the typical examples of you want to predict house prices based on properties of a house. So how do you embed these properties into a quantum circuit? There's a couple of approaches. We list them here. So say amplitude embedding, where you end up encoding features, your data set, the features of your data sets into the amplitudes of the quantum state. This one is quite efficient because you can fit in an exponentially large data set into an n-qubit circuit. But there's also questions of how to actually implement this efficiently. So it's a bit of a double-edged sword. There's also angle embedding. So this is just each feature in your data set gets mapped to a qubit, to a rotation of one of the qubits. And there's a whole lot more. So there's different ways, different practices on embedding quantum data. You can probably check out on the PennyLane documentation, but there is one established one, which is this angle embedding that I wanted to mention here. So this is, if you have like, say, an n-dimensional data set coming in, you map that to an n-qubit circuit, and each qubit kind of captures one of those features through a rotation. So this is a very simple way of embedding data, but how well does it actually perform? So I wanted to share another result that we had, I guess, maybe about a year or so ago. And I guess the temptation is maybe to encode the data at the start and then have some processing layers and have some measurements at the end. And that's what we've kind of alluded to already in the talk. But it turns out it's actually quite an interesting result. It turns out that it's not, or typically not sufficient to do this. So you can see in this diagram here, taken from this paper by Maria and team, if you end up just encoding data through one layer, then you actually really just fit a sinusoidal function plus a phase. So it's not, the circuit that you'll be able to train is not very flexible. Actually, what you need to do is you need to encode your data in multiple layers. So you can see here in the second figure, where we have 3 X's. So this would be 3 data encodings, and sandwiched between that, the smaller circular squares. These ones, I say, like the controllable variational layers. So by doing that, by having this repeated way to encode the data, we actually get much more flexibility in the model. And as you add more repetitions of this encoding, you get increased flexibility. So yeah, just to share this result. So that was a bit of a lightning quick tour of variational quantum circuits and what we try to do with them. And I want to, in the rest of or my section of the talk, to show you how this can be done in PennyLane. But before we go on to that, I just wanted to take a step back and say it's still early days, and there's probably more questions than answers at this stage. So things like, what are the best practices for shaping these variational circuits? How to typically structure them? What sort of measurements do we need to do? There's questions on best choice of optimizers. We're typically, I guess this is the first point, we're typically still running on simulators. We do want to run on these 50 qubit plus hardware devices, but we're stuck with simulators for now. Still questions on theory. There's lots of software libraries out there, so I'll talk about PennyLane, but there are other quantum machine learning libraries like TensorFlow Quantum. They're all good. They all have their strengths and weaknesses. And yeah, we're just edging towards hardware runs at the moment. So it's even a challenge to say to just evaluate a gradient on hardware rather than training a whole model. So it's an exciting field, but don't get too excited yet. Okay, so
maybe before we go ahead, there are a ton of questions that have been coming up on the chat. I've been answering some of them, but there are really a lot of them to answer. So maybe we can stop for a second and answer some questions.
That sounds good. Yes, let's have a question session.
Okay.
Great. There is a question from Domion Big. Does the repeated encoding of the data cause problems to the increase of the circuit depth in NISQ quantum computers?
Sorry, I lost how to unmute myself. Yes, I think it's a challenge for sure. The increased depth, the increased number of encodings will increase your depth. So yeah.
Okay, good.
It's a decision on how much do you want to pay versus how much do you want to have a flexible model.
All right. I guess the general question is how VQE compared with classical algorithms. I believe VQE is NISQ feasible, but may not be competitive with classical algorithms.
So VQE, VQE and QAOA, I say, are definitely the NISQ candidates for a nice application of showing something useful from quantum computing. How it compares to classical, I think it depends on how. I mean, we're still running mainly on simulators, right? So it's not really a fair comparison. And the hardware that we try and run on is fairly noisy. So I don't think we're yet expecting to run on quantum hardware a VQE algorithm that outperforms what we can do classically. But I think eventually we do expect that. And part of the motivation for this expectation that running on a quantum device will outperform classical is that it's actually a simulation of a quantum system, right? So we're not doing something like machine learning where it's classical data and it might be questionable about quantum versus classical and what's doing better. This is fundamentally a simulation of a quantum system. So that's where the motivation that in principle, if we had error-free or low noise hardware, it should be doing well.
Okay, there's a question from Carlos. Is that one analog to a polynomial curve fitting? If we increase the polynomial order, we can get a better fit, but also the chance of overfitting.
It's a good question. Yeah, I'm not sure about overfitting. Yeah, potentially. My interpretation from the paper was that you get greater flexibility, but I'm not sure maybe if you increase the depth, you may end up with overfitting. It's a good question.
Okay, good. There's also a question from Karim. Karim, would you like to unmute yourself and ask? Because I'm not sure if your question is already answered by Catalina. And so, Karim, would you like to ask a question? You're muted now. If not, then there's another question from Vasim. Is a gradient actually being computed, or this is just a convenient way to talk about the quantum system minimizing its energy?
So, yeah, a gradient for sure is being computed. Even if you're running on classical simulator, I guess it's not a true quantum gradient of a quantum circuit, it's a simulation of that. But yeah, you can get a quantum circuit, run it on hardware, and do a forward shift and a backward shift on hardware and post-process through this parameter shift. And this will be an approximation of the gradient. And this gradient is then used as part of the optimization. So yeah, I'd say for sure a gradient is being calculated. The end result is that we end up using that gradient to minimize the expectation value.
Okay, thanks. There's another question. Can you elaborate more what is squeezing state encoding?
Oh, yes. Am I on the right slide for this? The squeezing embedding, maybe? Yes, so at Xanadu, we have, I guess we're a full stack company, so we also have a hardware offering, and our hardware side is photonics based. So in our photonics system, there's a couple of ways to describe it. You can kind of map photonics to qubits, depending on, I guess, how you set up the system, but you can also map photonics to what's called a continuous variable system. So in this system, you have a different set of gates, you have a different set of operations, and yeah, this is what the squeezing embedding and displacement embedding are going after. So this is a CV or photonic based set of gates, and yeah, you end up having these, I guess, modes of light that have this distribution, this Wigner function that you can squeeze in certain directions, and you can squeeze, you can move it about. So yeah, maybe just to think of it as a different set of gates for photonic systems.
Okay, so Carlos has a question. So Carlos, can you please unmute yourself and ask?
Hello, great talk so far. Doing very good.
Thank you.
My question is, in the past, I run some experiment, like a real cold atom experiment, when then I have to feed a lot of parameters to maximize like the obtain of a Bose-Einstein condensation, a BEC, right? And then to be able to optimize those parameters to get like the best outcome, I use like a machine learned gradient to do that. In that scenario here, what is the difference of using a machine learning on the quantum computer and then maximizing the parameters you're feeding the quantum computer to get your cost function from when I try to optimize the parameters that's feeding to my experiment to get the best Bose-Einstein condensation?
So yeah, I'm curious in your experiment. So how are you getting the gradient of your system?
Every time I take a measurement of the Bose-Einstein, and then I compare that one with the previous ones by changing the difference between the parameters. Exactly the same thing you are doing here. You have like, you run your machine once, your quantum machine once, then you run again, and then you take the gradient. And then you fit your loop to be able trying to get like your cost function. Correct?
Yes, that sounds very similar, yeah.
Yeah, and my main question is, there is something else going on in the quantum circuit, or the learning is happening actually on the parameter space in the classical computer?
Yeah, I'd say it's definitely a hybrid. The learning part, the optimization part is, I guess, distributed to a classical device. Yeah, so it's, in a way, it's just a function, right? So there's a quantum circuit that's mapping from input data and parameters to some output number. It's just a function, really. And we just know that we can get the gradient of this function through parameter shift. And a classical computer can handle the evaluation of the, I guess, the updating of the parameters via the gradient. So yeah, I'd say you're probably doing a very similar activity, maybe using finite difference as your gradient method.
We actually use few different uses, also Gaussian distribution, to be able to learn the parameters.
Cool. Did I answer the question? Sorry.
Yeah, no, no, I got very clear. Thank you so much.
Cool. Thank you.
It looks that Catalina would like to say something.
Yeah, I wanted to add that what you mentioned, Carlos, sounded like finite difference. So maybe, Tom, if you go back to the slide where you compare them, you have to be careful because the shift in parameter shift can be a large shift. Remember the cosine example? It can be a very large shift, while in finite difference, it has to be very small. So in your classical way of calculating the gradient, you might be actually using finite difference under the hood, which has pros and cons, but you have to be careful of what the cons are. It will depend on your application.
And it's actually in that experiment you're using a Gaussian distribution to get the learning parameter space, and then after you got a learning, then you go to find to be able to try to find the optimal global. You have a learning space with parameter.
Cool.
Okay. Do you wanna go ahead, Tom? And maybe you can leave the other questions for in a little bit.
Yeah, we have several more questions, but maybe it's a good idea to just go on and.
We do have a Q&A session,
Yes.
hopefully, depending on how the time goes. So yeah, we can definitely answer some more questions there. So this part, I want to give a chance for everybody to actually either see me doing some PennyLane code, but more preferably allow you to do some coding and some quantum machine learning in PennyLane. So you may have seen in the invites, there was a chance to sign up to Xanadu Cloud. And the idea behind that, or at least one idea, is that you can visit this URL here, and I'll paste it into the chat as well. If you visit this URL, there's a hosted notebook that will let you follow along with what I'm about to show. So if you already have a Xanadu Cloud account, you can go to here. Let me just paste this whole slide into the, into the chat. Where is the chat? Maybe Catalina, can I paste it to you and you'll paste it in the chat? Sorry about this, guys. Okay, so I've just sent it to you, Catalina. Thank you. So those are the links. Yeah, the idea is if you already have a Xanadu Cloud account, you can go directly here. You'll need to sign in. And then you get the notebooks. If you want to make a Xanadu Cloud account now, feel free. We have somebody that's waiting to sign you up. So yeah, just fill in this form that you made that was shared around earlier. You should be set up in 5 to 10 minutes, depends how it goes. Just need to give your first name, last name, and email address. And then you can go to this, this address here at the top in step 1 and access the notebooks. If you don't want to make a Xanadu Cloud account, that's totally fine as well. You could clone the repo or just feel free to watch, follow along. So lots of options, but hopefully there's a chance to be interactive and follow along as well. So, okay, now I will click this link. So yeah, just to show you what's going on, you need to sign in. And hopefully everybody should see this loaded up when they get a chance to sign in. So this is, I guess, just like a hosted notebook that has PennyLane preloaded. So when you click here, it has the PennyLane environment set up. What we need to do, this is just a slightly annoying step, so I apologize for this, but we'll need to clone the repo that has the demos. So when you get to this step, just copy this thing here. You'll need to, just to show you again, you need to open this terminal down here and paste in, Control V, this command here, and it'll clone the repo, and you'll see it just pop up here. So feel free to ask in the chat. I think Catalina or Mikhail may be able to help. Mikhail's the person that's helping with the signups. So if you're stuck on that step, we can hopefully help. But once you're there, you should get to these notebooks. And there's 5. We won't get a chance to go through all 5, but I wanted to include them. So if you want to, after the talk, we'll keep the service rolling for about a week. Nothing guaranteed, so use it maybe sooner rather than later. But yeah, you should get some access at least after today. You can try out these demos if you like. So without further ado, let's check out this first demo. This demo is just really the basics of PennyLane, so setting up a circuit and running it. By the way, if you do have some thoughts on how this part went in terms of this live demo, you can fill in the survey here, much appreciated. So, okay, let's get started. We've seen earlier in the talk that in quantum differentiable programming, we often think of these hybrid models where we have classical and quantum nodes. Let's zoom into one of the quantum nodes, so one of these blue boxes, and just set up a simple example Q node. So suppose we want to run this circuit here. It's a circuit and we can run it and we can get its derivative. And we're thinking of this as the Q node within potentially, I guess we're not setting it up in this slide, but within a larger computational graph. So in PennyLane, there are 2 ways to, two components of a Q node. There's the device, and there's also the circuit that we're going to run on the device. So let's set up the circuit first. Actually, we'll begin with the standard inputs that you'll see in PennyLane. So this input PennyLane is QML. This is just, I guess, the established way that we suggest to input PennyLane. You'll see this second line here from PennyLane input NumPy as NP. This may be a bit less familiar to everybody. If you've used Python before, maybe this one's the standard. So the reason we have this extra importing NumPy from within PennyLane, this is to support differentiability. So the PennyLane version, which is based on a package called Autograd, this supports differentiability if you use anything like numpy.sine or any NumPy-based functions. If you didn't do that, then it would break the differentiable pipeline. So familiar things you'll see when you do an import. So now we want to load our device. And this is the standard command that you'll have in PennyLane. You have a qml.device. You pick a name, and there's lots of devices that you can run in PennyLane, lots of different backends. We'll talk about that a bit more later. Here we're using a simulator device. We're using one called default qubit, which, as you might expect, is kind of the prototypical device for quickly making models, trying stuff out. There are probably better devices if you want to have a lot of qubits, or if you want a very like a purpose-built device for certain types of computation, but this is a nice general purpose one. So we're loading this device. Now, the other part of a Q node is the actual circuit that we want to run on. And in PennyLane, this is described via a quantum function. So we just have a standard Python-like function where we have the parameters of the model. So here we have theta, phi, and omega, and we line up our quantum gates within the function. So you can check out the docs here for, I guess, a summary of all of the gates, the qubit gates, and we also have these continuous variable photonics gates as well. So, okay, what do we have here? So in this circuit, it's just an example circuit, nothing too advanced. We have some rotations. So we have an X rotation, Y, and Z rotation on 3 qubits. And this is how you do you describe that within a PennyLane quantum function. So we have QML.Rx, our Y and our Z, and then we have a cascade of C0 gates coming through. We finally, so we know that we need to do a measurement to extract information from the circuit, and this is via return of the function. We return the expectation value of an observable, in this case, a Pauli Z observable. So this is our circuit. Now we have the 2 components and we want to bind them together into a Q node. That's this line here. So we have QML.QNode pairing together the circuit and the device. So this, our Q node, this variable here, this now looks like a function that you can call, evaluate it, and you get the result of running the circuit on that device. We can see that just here. We load some example parameters. We evaluate the circuit. It's just a simple number for now. It's a fairly basic circuit. But yeah, this is a nice example of pairing the 2 things together, device and circuit, and getting a result. There's also other stuff you can do. So you can print the circuit. This is using our text-based drawer, but you can also draw it using matplotlib. So yeah, you can see they kind of match up. So now we have a QNode, and we've seen how to create it using this QML.QNode class. I wanted to mention another way that you'll often see if you check out tutorials in PennyLane, so that you don't get confused. There's a decorator approach as well. So this way lets you quickly move from a quantum function to a quantum node, to a QNode. All you need to do is get your quantum function and wrap it with this QML.QNode decorator, which will then pair this device to the circuit. So if we evaluate this, now circuit 2, this behaves like a QNode. So we can call it, we can evaluate it, and we can draw it as well. So these are the, I guess, the most elementary steps of PennyLane. I wanted to mention as well, we talked about picking a device, a default qubit device. It's fairly easy to swap out the device. So maybe you have a circuit and you train it in default qubit, or you set up your model, you're happy with it, and you want to then run on quantum hardware. How do you do that? Well, what you need to do is swap the device. So you say, okay, we're done with default qubit. Let's swap it for another device that's a hardware device. You can check out all the available devices by going to this link, this plugins link. There's some built-in ones. We also talk about plugins, which are external packages that you can install that supports, I guess, the usual providers like Qiskit, Bracket, Circ, and a couple of others as well. So here we're showing how to run circuits using Qiskit. If you run this cell without changing it, we'll run on Qiskit's simulator, this Qiskit Air device. What I'm going to try and do here is this version, if you comment this and uncomment this one, this version will be running on a remote Qiskit device on IBM Q. So if you then swap this out, you can actually change this to be a hardware chip. I won't do it here because there's a queue, so we may end up waiting a while. But yeah, here, if we run this, we'll actually run on a remote server somewhere in one of IBM's servers. So, okay, let's load this device. So if you want to do this stage, if you end up changing from here, you'll need to put your IBM Q token on this left-hand side. So no worries if you've not got it set up, just use this version. But if you want to paste it in onto here, then you can run on this device. So, okay, we've changed our device. We can pair the QNode, you can get the QNode by pairing the circuit and the device together again, this being the new device, and we can run. So there we go. That was actually rather quick. Did it work? Oh, okay, I think it didn't spot the device. So now let's see. So now we have the new device. It takes a bit longer, again, because it waits in the IBM, the Chasm queue. But yeah, you can see the result has come back. So it's as easy as swapping from default qubit to one of the other devices. And yeah, there's other things you can do. Instead of just returning expectation values, you could return a probability distribution. So there's other return types in PennyLane. So that's the first demo. There is I possibly have time for a second demo, but I want to pause for any technical questions. Maybe we could defer any sort of QML quantum questions to later, but is anybody struggling with getting stuff set up? Hey, JRM.
So I don't really know how to access this thing. This how do I and I requested access, but told me to change my password and do all those things, but I still haven't gotten access to the PennyLane coding.
Okay, so if you've made an account, did you click here? I think that was hopefully pasted in the chat. Did you go to there and have any troubles?
I think. Well, okay, let me try. Yeah, like it tells me to log in, but like I do not know how to create my account.
So I guess, yeah, the first step is if you made an account, did you set a password?
Well, actually created an account, actually, never mind. But like, yeah, but like, actually, let me try to do that again one more time.
Cool. Okay. Yeah, maybe for that one we can help in the chat. Any other questions? Any big issues? Has anybody managed to get onto here?
Okay, do we have any more questions? Jairam, your hand is still raised, but I guess that your question is already answered. So, okay, thanks.
I think somebody has a question on how to upload the files once they have them. I think that's
Okay.
Samar's question, right?
Thanks, Catalina. So if I understand correctly, you're probably at this stage. So you've managed to get in, but you don't see this folder here. So the next part is to just load up this terminal down at the bottom here. And so you see it come up. You just need to copy this bit over. So Control-C, Control-V into here. And I'm not sure what will happen for me, but it will get that folder to come up down here. So hopefully that works for you.
Okay, thanks. All right.
Excellent.
We have some more questions. We have some questions that were just posted several minutes ago, so we can go back, but maybe there are some questions related to what Tom has been recently presenting.
So I think I have maybe 5 minutes to quickly go through this, and then we can maybe transition to Catalina showing the codebook. I can also help out in the chat if people have issues with this.
Okay,
Hello?
good.
Hello? Hello,
Yes.
please share the presentation that you show now. I don't have I attend somewhere late. Please share the link of the presentation. Thank you.
So we can share these
we've-
slides and so go ahead.
Yeah, so I wanted to say that this meeting is recorded. So as usually, the video will be later shared. So don't worry. And the slides will be probably also shared. I'm not sure, but if you share the slides with us, then I believe that Helen will distribute the slides among participants.
Yeah, that sounds good. And if you're stuck getting here, if you're already in, then just open this terminal and run this command. I know it's probably a bit of a pain, but yeah, if you just copy paste that, it should work. Thank you. Okay, let me just run through this part. I want to talk about gradients because that's the cool part of PennyLane. So far we've seen how to get a circuit, how to evaluate it, how to maybe draw it and swap out the device. But how do we get a gradient? How do we train? So suppose we have the circuit. It's essentially the same as before, but we just swapped the measurement to the bottom qubit. So this is our circuit now. We know how to create a Q node for this circuit and how to evaluate it. That's what we have in this code block here. So we usual imports, load the device, it's a 3-qubit circuit, create the circuit and bind from circuit and device together to make a Q node. How do we get the gradient of that? So there's a couple of ways to get gradients, and in PennyLane we have support for TensorFlow, we have support for Torch and for JAX, so these differentiable programming libraries. But maybe the default standard way in PennyLane is to use this QML.grad function. So this QML.grad function, we apply it to our Q node. And remember, the Q node is just something that looks like this F of theta, phi, and omega. So we just apply to this Q node, And the thing that we get back is another function that essentially just gives you the gradient. So if we run this, we see now we're not getting the result of the circuit, we're getting the gradient of the circuit. So that's the derivative of the circuit with respect to the parameter theta is the first entry, then phi, then omega. So yeah, this is how to get the gradient. There's also a question of, okay, maybe we can get a gradient, but typically when we do machine learning or these optimization-based problems, we don't just want to get the gradient, we want to optimize, we want to minimize the cost function. So how do we do that? Well, that's a case of, let's create a cost function. Here, we're keeping it simple, we're just calling the cost function, just making it the same as the Q node, but you could do something more advanced, and maybe in other cases it makes sense. I know you can do like a, stuff like this. You can process the value of your Q node. You can even create a sign of it. As long as everything you do in this cost function is differentiable, you'll be able to train it. But let's just keep it simple for now. So then to train, we load up an optimizer. So there's a couple of built-in optimizers. You can click this link. Here they are. So let's use the basic gradient descent optimizer. So we load an optimizer, PennyLane optimizer. Then we run a standard optimization loop. So each step in this loop, we're evaluating the gradient. And so we're doing gradient descent. So we're sort of navigating slowly down this hill. So we'll do that 100 times, 100 steps in the loop. And it's such a simple circuit, it'll run fairly quickly. If we evaluate the cost now, I guess we didn't print it earlier, but the cost would have been some random. So this is the expectation value we're calculating that's constrained to be between -1 and 1. So the cost function at the start would be some number in between this in this range. And we're minimizing. So we've run gradient descent optimizer to minimize this cost function. And you can see that the result, once we've optimized these parameters, theta, phi, and omega, is we've managed to minimize this cost function. So we've got to -1, which is the smallest possible value. So we found both the minimum value of the cost function, and you can also see if you print theta, so it's now different. It's an optimal value that's different from what we loaded before at 0.1. Same for phi and omega. So this is a standard optimization loop. It was for a super simple circuit. In reality, we'll mix this up, right? We'll return maybe a Hamiltonian in here of a chemical system or of an optimization problem. But just for the sake of example in this notebook, we kept it simple. And yeah, here we have a nice plot of, you can see the cost function went down. So how did we actually get the gradients? And in PennyLane, there's a couple of ways. So since we were running on a simulator, you can see we were running on default qubit here. This is a simulator, so it is possible to get a gradient through classical backpropagation. So that's what happened in this optimization loop, just here. But of course, we need PennyLane to be compatible with potentially with hardware. So how do we get a parameter shift gradient? So this part is just to mention that. So this is the gradient using backpropagation, just here. If we manually calculate the parameter shift using this rule, you'll see that the gradient for the first term, this matches here. So this is the gradient of the circuit with respect to theta, and we get it to match. So this is a manual calculation. But if you actually want to just automatically calculate the gradient in PennyLane through parameter shift, you just need to mention it here with this diff method. So it defaults, if compatible, it defaults to backprop. But say if you're running on a hardware device, this might change to parameter shift, or you can fix it yourself to specify parameter shift. So now it's, yeah, maybe it looks unremarkable because it's the same as this, but it's a fundamentally different way that we've used to calculate the gradient, this one being backprop and this one being parameter shift. And I have a section on quantum aware optimizers. I'm aware of the time, so maybe I'll let everybody check this part out in their own time. And there's also some cool demos to go further with. So this one's a machine learning one. For a simple data set, you can classify 3 different labels. it's a classification problem, VQC. We have a quantum chemistry problem for demo 4, and also a Qaoa problem for demo 5. So yeah, hopefully you got a bit of buzz from these 2 demos, and feel free to try these out. The service will be online at least for a few more days. So hopefully lots for you to enjoy. Yeah, that's probably it for the live coding part. I'll probably hand over to Catalina now. We had a couple of things just to mention what we're excited about for the next PennyLane. Just check out some nice drawing functionality. If you want to know more, feel free to go to PennyLane.ai. We have demos and we really prioritize our documentation. So our objective is to keep things as accessible as possible. But if you really want to know more just from understanding quantum conceptually, you should check out the codebook, and that's what's coming up. So just before I hand over to Catalina, this is just to mention we have a QHack coming up. So this is a hackathon. It's a community event focused on quantum machine learning. This is happening actually pretty soon in 2 weeks' time, starting. And we're going to have a mixture of live talks. You can join in, you can message in the talks. So it'll be really interesting. And we're also going to have a hackathon section. So this will be like, we'll set a challenge. Everybody tries to solve this problem. So that would be cool. And we'll also have some coding challenges. And that's a bit I really enjoy. So in these coding challenges, we'll set little problem tasks and people can try and solve them. There's a leaderboard. So if you're competitive, it's great for getting lots of points. So yeah, feel free to check it out. It's free to register. So yeah, just sign up if you're interested. And now I'll hand over to Catalina to talk about the codebook. Feel free to message me in the chat if you have questions about the platform for the demos.
Great.
So thanks, everybody.
Great. Thank you, Tom. Thank you. It was a really great presentation. And indeed, we have some questions on our chat. So if you can now just answer at least some of them on chat, that would be great. And yeah, Catalina, the Zoom is yours. So if you're ready.
Thank you.
Please go on. Mm-hmm.
Yes, thank you. So just to answer some of the questions, some people were experiencing an error, so we will look into that. So for now, we hope you could enjoy Tom's demos, and hopefully it will be solved very soon. Somebody had a question about their t-shirt for QHack being delivered. So the first 100 people to have registered, they got a chance to get swag from QHack. It does take some time to get that all around the world. So unless you're in Canada, which is where we ship them from, they will take some time to arrive. So don't worry just yet. If you don't get them in a few weeks' time, if in 2 weeks or 3 weeks you still haven't received your t-shirt, then please do send us a message. You should have received an email asking for the swag, so you can respond to the QHack email, or you can contact us on Slack, or we have a different means of contact. So hello@xanadu.ai or Slack, etc. So now going to the topic of the codebook. Let me share my screen. Okay, so for those of you who maybe felt a little lost on some of the details today, there is an interactive codebook. So we call it a codebook that will help you. And for those who are advanced, who already know part of what Tom talked about today, this is also for you. So today I'm gonna talk a little bit about the motivation behind it, and hopefully you can get interested in this. So I've shared the link before, but maybe Tom, if you can share the link to the codebook again on the chat. If you're looking at the chat, that would be awesome. So today, quantum education happens, a lot of it happens in universities. It's focused on graduate students, and it focuses a lot on theory. So you might be a physics student who knows a lot about the theory of quantum computing, but you might want to actually code this, right? So we created this tool that allows you to learn at your own pace, and that allows you to actually engage with the content. There are a lot of excellent books and textbooks around But it's more interesting when you actually do something hands-on, or when you're challenged with a problem and you don't have the exact answer at hand. You have to look for it, you have to try, make mistakes and learn from them. So this is the context in which the codebook was thought of, and this is how it will help and be different from other resources that you may already have seen. It's not only limited to people learning on their own. It can also be used in a classroom, but it is a completely different way of learning than just reading, right? It's based on actual education theory. So for adults learning, you need these principles that allow you to be engaged with a learning material, right? And you need to be able to learn it at different times. You will necessarily have a teacher with you to help you learn. You can go check it out at codebook.xanadu.ai. You might have to accept some terms of use, but then you can use it at whatever time you want, and it will keep your how much you have advanced. So it will help you progress little by little, right? You can begin at whatever level of expertise. So here we have an example of how an introduction node looks, right? But there are other more advanced ones. There are actually 3 new nodes that were released today, and I will mention them at the end. There is a little bit of a background that we expect from people using this codebook. We expect people to know Python, basic Python, and a little bit of linear algebra. So for the concepts that you might have learned at an undergrad course or a high school, or maybe on your own, there are a ton of resources available online if you don't know Python or if you have no idea about linear algebra. But the basics that we expect from people using this are really not much. So you can also learn these even by exploring the codebook. We also have a left pane where you can navigate, and it's a sort of a graphical tool to see how you're doing, how many nodes you have to complete a module. We have a left pane that includes coding exercises, and then on the right you will see more like classical textbook kind of content, where you can go in depth if you're not being able, for instance, to solve the challenges that are here on the left. Then you can go to the right side and read more about it. Or if you are interested in learning the basics of what you're doing here on the left, then you can go and check out the right side. You can also hide it if you prefer. We're focused on actually being able to apply this. So this is software that is being used in research and industry. PennyLane is being used today by people in the front of their fields. And we want everybody to be able to access this knowledge and to access this practical experience of programming quantum computers. We also wanted to use a tool that people already know. So many people already know about software development in Python. So this tool is used to learn something new, right? To learn from beginner to advanced topics. Here on the left, you see the current structure of the codebook. So it has a tutorial node, has an introduction node, it has an algorithms node. It says quantum Fourier transform, phase estimation, Shor's algorithm, Grover's algorithm, and I think the others Hamiltonians. So you can see that there's a wide range of topics that you can learn, and you can choose how to learn it. So if you feel that you don't need to learn the introduction part, you don't have to. You can go straight to learning about Shor's algorithm or Grover's or whichever you prefer. You decide what to read, when to read, what to code and what not to code. On the right-hand side, look, the classical textbook side, let's call it, you will also have like pen and paper exercises, and you can decide whether or not you do that. And for the coding exercises, you will also have the motivation that as you complete them, your nodes will turn green. So somebody asked before, will you get a certificate for completing the code book? The answer is no, but if you really want to show off that you have completed it, then you can take a screenshot of your navigation pane on the left and show everybody that all of the nodes are green. Something that is very important also is that we learn, it motivates us to learn when we know that we can solve a real problem with whatever we're learning. So many of the modules are made with real examples. So you will find examples that are sometimes beginners, like the algorithms, you can break a lock, let's say, but some of them are like more advanced, and these are things that are actually being done today, real examples. You don't have to wait for somebody to grade your exercise. It's auto-graded, so that's cool. And you will also get little messages at the end of it's correct, or you made this error, or this other. But if you do have a question, you're stuck in a problem, you can go to our discussion forum, and I will show you in a minute how to get there. And you can ask your questions. It's very important. You will get your progress recorded with these green, the green color in your notes. But if you clear, I think it's your cache or your cookies. I mean, if you don't let us track you, then you will lose your progress. Okay, so be careful about that. And I'm gonna show you how the code looks like. You should be seeing the code book, right? Tom, maybe?
We can only see the slides, not the
Yes.
Okay, let me share again. Probably need to reshare my screen. Maybe now?
Yes, it's fine.
Okay, good. So when you go to codebook.xanadu.ai, this is the first screen you'll get. Here, that's where you get the information of where you can provide feedback and stuff. So we can go to it on the X on the top left corner. If you need to provide feedback because there's a mistake that can happen, you can go to our GitHub repository, or here you can find the discussion forum, where you can let us know, I'm stuck at this node, I'm trying this, I'm not sure, I've tried it a lot, and I'm not sure why I'm getting an error, right? So we'll try to help you, but we encourage you to try to solve your problems on your own. And if you're really stuck, then you can ask questions here. If you want to give us feedback, please, we welcome it. There's a forum here linked so that you can give us feedback and that we can make this tool better for everyone. Okay, so here on the left, you're going to see all of these nodes. And the first thing you should probably go to is our tutorial node. So you can click on the nodes here on the left, and you will see on here that you have a challenge that you need to solve. Let's say this one is adding two numbers, right? Create a function to add two numbers. So I can add my code here. Say it's x plus y, return x plus y, and then on the bottom I can click submit. Now we'll get a message that says correct. And then more content will be unlocked. So before I couldn't go down, now I have more information mode, more coding exercises that I can solve. And on the bottom, you can see how much of this node you have completed. On the right, you will see the text kind of information. And you can find these exercises with solutions that you can just click on the arrow and see the solution. I'm gonna go back to the modules, to the introduction one, and you can see how the other ones look. So again, this node has five coding exercises, and on the right you have more information. So I do encourage you to try it out, to give us feedback, to let us know what you think about it. This is very, very good material. It's really it has a lot of thought into it, and it's been really useful to many people. We have thousands of users who've used it already. Last time, at the end of last year, I think it was over 2,000. So would love for you to be able to take advantage of this resource, which is available free whenever you want to use it. And it has from beginner to advanced content. Okay, so I will stop sharing again so that I can go back to my slides. Okay. So today we added 3 new modules: quantum Fourier transform, quantum phase estimation, and Schrodinger's algorithm. So the ones that you see with a green circle on the lower right of this image. So if you have used the codebook before, and maybe you've finished all of the other notes, this is a good chance to keep learning. So learning always continues. These are the ones we have added today, but we have planned updates to add more in the future. So keep posted. Do follow us on social media, on Twitter, on LinkedIn. We do share this information with the world. We want everybody to be able to use it. And if you want to cite this textbook, this codebook, you can. This information is also on the main node, on the little X on the top left. I want to mention this work was guided mostly by Olivia Mateo. She's working at UBC, University of British Columbia. David Wakeham as well worked a lot on this, and many other people. This is really a team effort. This is a huge project, and we hope you can use it and enjoy it. Maybe before we leave, I want to show again the QHack site. So let me show you what QHack is all about. Okay, you should be seeing my QHack screen now. QHack is the quantum event of the year. You can sign up here, and you can learn more about it here on the top. You can see the trailer, the events. We have a lot of events happening. The main 3 are the streaming sessions, the hackathon, and the coding challenges. You can look at the prizes. They are also incredible. And there's a little bit for everyone. If you want to see who are the sponsors, it's basically most or all of the major players in the quantum space. And excellent speakers from a ton of different companies. So here we have Zapata, IBM, Uniter Fund, AWS, Alphabet, Google. I encourage you to check it out. So just qhack.ai. If you have LinkedIn, you can also look for the event in LinkedIn and then add it to your calendar. So with this, I think it's time for Q&A. There surely are a lot of questions here, so feel free to ask them.
Okay, great. Thank you. Thanks, Catalina. So Tom has also already answered some questions. Do we have any more questions? So there is one question about the syntax difference between this language with other quantum computing languages. There's a question from Dev. Maybe he would like to clarify. Because here, in fact, we rather have a framework, but yeah, Catalina, please go on.
So you will see a couple of differences. One, we use wires. We talk about wires instead of qubits. So this is something that is different to other frameworks. Many of them are in Python. So if it's not in Python, that's a big difference. But if they are in Python, some differences that you will note is that other frameworks don't use Q nodes. Here we use a Q node, which you can use a decorator to make your Q node, or explicitly say like qml.q node and then add your circuit there with your device. So the Q node basically ties up your quantum circuit, which is a Python function, to a specific device. You have like different kinds of measurements, so that will also be different. You will might notice that we have expected values. You can calculate it super easy. Just use qml.xval and then add your qml.operator, poly z, poly x, whichever you want. I'm sure I missed like a lot of stuff, but these are ones that you will notice like straight away. I don't know if you want to add any, Tom.
Okay. So Dev, I hope that it answered your question, but if not, then please also just post a follow-up question. Yes, there's a comment from Zoom caller. It's a framework. Every company has their own. Python is Python as a programming language. There are programming languages like Q#, for example. But basic ideas are more or less the same, but also Catalina has explained what are the differences in terms of the framework from Xanadu comparing to some other frameworks as well. Okay. Great. Do we have any more questions? So some questions that were posted before are already outdated. There's another question.
I see a personal direct question. So if I'm doing quantum machine learning, what is the effective and faster way to do backpropagation on actual hardware and not a simulator, since there's no cloning theorem in quantum systems? How do you bypass that for backpropagation? So I don't know, Tom, do you wanna get this one? As far as I know, backpropagation doesn't work on hardware.
Yeah, it's a great question. So there is a motivation to want to do backpropagation on hardware because parameter shift scales a bit worse. So there's kind of, for the number of parameters in a circuit, you have a quadratic scaling with parameter shift. With backprop on a classical simulator, it's a linear scaling. So actually it's sort of square root faster. So there's a motivation, but the answer is I have no idea. It would be an awesome research result if we could do it, right? I think there's not really an intuitive way that I know of how to do backprop, at least in its current form, on a classical simulator, exactly mapped to a quantum circuit. So it would have to be something pretty smart, probably with lots of ancilla qubits.
Yeah, I think that's a great answer. We have another question. Where do we need API key? So this was probably from your demo, Tom. You need the API key in order to use the Xanadu Cloud. So I don't know if we want to give any details about that.
Yeah, so for the service that I showed, you shouldn't need an API key to just sign in. There's two API keys we might talk about. So there's the Qiskit API key. You'll need that if you want to sample from their hardware. You can paste that into, if you look, there's a left sidebar, the bottom one. If you go there, you can just paste that in and that will let you sample from their hardware. We also have our own API key if you want to sample from our hardware. Maybe I can send a message to give you details on where to get that from.
Great. Yeah. Someone says, I think the main difference is that you can differentiate hybrid classical quantum circuits. I'm guessing that was referring to backprop. Or I'm not, oh no, that was probably about the difference between PennyLane and other frameworks. Okay.
Yeah, absolutely.
Yeah.
I think that's a massive bonus. I
Mhm.
mean, I'm biased, but I think that's one of the key parts of PennyLane.
Yeah. Does Xanadu have programs similar to Qiskit Advocates? We don't have a Qiskit Advocate program, but everybody can become an advocate. So what do I mean by this? We do count on the community, and I'm part of the community team and the quantum community manager. So what we strive for is for that everybody feels welcome at our community. And I think this is some of our big success. We have managed to create a community where everybody is welcome. We have calls every Thursday at the Unitary Fund Discord on the community call voice channel. So if you follow us on Twitter, you will probably see the messages that we post on Wednesdays, where we talk about what topic we're gonna be learning about on Thursday. So every Thursday, we meet with the community. We love learning about you, like meeting you, and we teach a new topic every Thursday at 11 a.m. Eastern time. So there's not Qiskit Advocate program equivalent, but we do work a lot with people. We have an amazing demos page, and it has a special section for community demos, which means anybody who's not a Xanadu developer, but who wants to contribute something, some work that they've done, we showcase it there. We have events like QHack, so the community is super important for us there. We want everybody, each one of you, to share this with others so that more people can enjoy and learn and use PennyLane. We have a lot of contributors. We want you to make the software better and to be part of this world of open source. PennyLane is open source. It's by everyone for everyone. And we've seen amazing contributions. I have one in mind, which is relatively recent, where a user was starting like thermal relaxation error contributed like a full like new error channel to PennyLane, which was pretty awesome. So I don't know if this answers your question. Okay, I mean, Qiskit Advocate gets some help in getting remote internships and stuff. We don't make this like help specific to some people. So maybe that's like the summary. If you need help from us, come and look for us. You can ask questions in the discussion forum. You can come to the community call. You can attend our events. And as much as we can help you. We cannot guarantee that you will get an internship, but we welcome everybody and we try to help as much as we can.
Okay, great. Do we have any more questions?
Actually, I do have some intent about the event itself. So I wonder, do you have a kind of, decent requirements for these internships or, entry-level job requirements? So can you just inform about this, what do you expect from your, employees or, your teammates to be exactly what level in this quantum computing or etc., something like that?
Great question. It depends on each, on what you're applying for. So let me copy the careers page. So you can go to xanadu.ai, and then on the right, you'll find careers. So my recommendation would be go to the careers page and look for a career. Look for a job that sounds like you. They're usually like fairly open. So say my personal case, I had worked at IBM, but I didn't have like formal experience in quantum community management. I had done that as a volunteer for years. And that counted as experience because it doesn't have to be a company paying you for you to get experience. That is also a big motivation for you to contribute if you want to do software, for instance, if you contribute to our software, that I definitely encourage you to add that as experience, because it doesn't have to be somebody paying you for it to be experience, right? So go to that jobs site. You can access it through Xanadu.ai, and then go to the careers part, which is on the right menu, or you can go to the link that I also shared in chat. And I encourage you to look for what each job asks for, and try to make your skills aligned with that. I hope this answers the question.
I appreciate that. So actually, I'm doing an internship at Google Turkey currently. It's not related to the quantum field. I'm just trying to switch my field and get into the quantum software side. As they are just popular in that and calling the quantum developer side. So it seems there's a lot of opportunities, but it's not actually, they are not actually related to the exactly in the quantum mechanical field. So do you really actually suggest me to go for the master or PhD degree, or bachelor degree is enough for that?
So it's
knowledge of sides.
Yeah, it's possible that your exact expertise doesn't match any of our current opportunities. So what I would encourage you to do is to try to find a job that helps you develop the skills that will be needed for your dream job, whether it exists today or not. Some of the jobs that will exist tomorrow, we have no idea, but you should develop the skills that you like. If you don't like something, then you'll probably not be great at it, right? But also the skills that you think will help you get that job, that future job, which maybe today doesn't exist. Yeah, so if you have like a different job, it can be in a different company. So maybe the job doesn't exist today at Xanadu, but you can get those skills that you will need by doing something else.
I appreciate that. Thank you.
I have a question with regards to, a very general question with regards to PennyLane. And this with to do with the basic idea of machine learning per se. So let's say if you have a representation of certain points. So one is in the quantum space, you're looking at the state explosion where you got too many points, and therefore that's one area where you're trying to deal with in quantum computing. But then you have another area, and I heard that Xanadu is photonic based. So then I'm again thinking about the hyperplanes. So for example, if you got these points plotted, then how you can arrange it into different hyperplanes or maybe different spins, and then draw a line or some kind of aggregation on the feature set. Is that the idea? Are both of them included, or is only the state explosion involved in PennyLane Xanadu framework? Do you get my question?
Yeah, I think I get your question. I kind of interpret it as, is this advantage of using a kernel method compatible just with the qubit approach, or are we also using the fact that photonics is involved to also argue that it's kind of useful? Is that what you're asking?
Yeah, so I think that's part that is one part, yes, because obviously photonic part is one, but also one of the reasons why machine learning in quantum space is being pushed into is because of this state explosion, which quantum computing is able to handle. So that's one area. But then there's another side of this, looking at it from how well you could categorize these various points that are in your feature set, for example. Does this cover both the areas, or is it particularly suited for state explosion or something like that? Or are there any advantages to using PennyLane per se as to any other competing framework, for example?
So I have to admit, I don't know what state explosion is. So I don't know if that's a term that I've not picked up, or maybe it's is that an established term? Either way, yeah, I think the kernel methods approach is potentially amenable to the other providers as well. But at some point, if you're using the kernel approach, you're going to need to train it, right? So you're going to need to, you're going to have this feature space. You're going to want to move the points to start trying to separate them. So this differentiability is needed. So there, I'd say that's where the use of PennyLane comes from. And you can do this kernel embedding in both a photonic and both also a qubit-based setting.
Right. And are there any, so there's this, I'm just thinking it from the point of, how do I describe it? As an adiabatic computing type of environment, would that fit in this as well? Sort of energy variations kind of thing? Or low energy models and things like that?
I tend to think of where the adiabatic model comes in. It's closest to QAOA. So yeah, I'm not aware of how to elaborate the link with the kernel-based perspective, but certainly with QAOA, there's a lot of links to adiabatic. And there you have, yeah, you're minimizing the expectation value of a Hamiltonian, and you're doing this interleaved application of, in QAOA at least, you're doing this interleaved application of cost and mixer. It's very similar to adiabatic, where you have these sort of two phases that are interleaved. So yeah, I should check out that for understanding analogy.
Thank you for that.
Okay, great. Thank you. Do we have any more questions? No more questions on our chat, at least on the public channel.
There are no more questions. I would like to thank the organizers for organizing this meeting. It was a pleasure to be here. And we hope to be able to stay in contact. And for everybody attending, thank you. You had excellent questions. Really enjoyed being here with you. And we hope we can also see you at every other future event that we have.
Actually, somebody asked for the Slack channel for the Xanadu.
Yes, let me paste it.
Thank you.
Here, it should work. So if somebody can, I think I sent it to someone privately. Sorry. Sorry. Here, it should work. But if somebody can test it, just in case, because sometimes those invitations like expire. But if it should work, yeah.
All right. Great, fantastic. So Catalina, Tom, thank you once again. It was really great presentation and very informative, very interesting. So also the amount of comments and questions you can say about it. So yes, it was great. Thank you. Yeah, we hope to see all of you on our next meetings in February and March. So stay tuned and yeah, have a good evening, everyone. Thanks.
Thanks, everybody. Great to meet you. Great to discuss.
Thank you.
Thank you, everyone.